Hello and welcome to Stability and Frequency Response of Linear Systems video tutorial. In this tutorial we will learn MATLAB commands that can be used to determine stability and frequency response of a system from its transfer function. Before we start, let's learn how to use M files. So far we used command window to enter the code. Now we will be using a separate file to enter the code. Using a separate file is more convenient because if we need to change our code and rerun it, we can edit the code in the M file. If we work in a command window, to change the code we have to go to command history window, recall the line that we want to change, and as well as other lines that need to be rerun. Often it is not convenient at all. So let's create an M file. In MATLAB menu we go to File, New, Blank M file, and a new window will appear. Or we can just click on the symbol New M file. From the theory we know if a linear system is described by a transfer function h of s, the system is said to be stable if the poles of h of s are in the left half of the complex plane. For example, if we have a transfer function h of s equals to s plus 2 divided by s to the 5 plus 4s to the 4 plus 3s to the 3 plus 6s squared plus 8s plus 10, we can determine whether or not the system is stable by plotting the poles of h of s, roots of the denominator. First, the poles are found by using the roots command in MATLAB. The argument of the roots command is a vector of the coefficients of the polynomial going from highest order coefficients to lowest. So we have poles equals roots 1, 4, 3, 6, 8, and 10. The poles can be found by plot real poles, imaginary poles, x command. By default, MATLAB connects data points with a solid line. The x string in the plot command tells MATLAB that we want each point marked with an x and no connecting line. Now let's run our M file by clicking on the green triangle. MATLAB prompts us to save the file, and let's name it stability and save it as type M files in the folder Stability and Frequency Tutorial. Afterwards, MATLAB prompts us a window saying that it cannot find the file. If we look into current directory window, we see the folder that we saved our file in, but not the M file. So in order for the MATLAB to run the M file, it has to see it in the current directory window. Let's click Change Directory button. Automatically MATLAB goes into the folder where we saved the file. So now we can see in the figure 1 the plot of the poles. And there are two poles on the right half plane. This means the system is not stable. Now let's go back to our M file editor and see how to do the same thing with a built-in command for generating pole zero diagram in the control system toolbox. First, we will disable our first two lines by writing a % in front of them. The lines changed color to green, and for MATLAB they look non-executable. This is actually the way to write commands in MATLAB. Second, we will define our transfer function in MATLAB with a command tf. Vectors of their coefficients specify numerator and denominator of the transfer function. Third, pole zero diagram is generated by pzmap h of s command. As you can see, we have the same plot as in the previous example, except for on this one we have also a 0 at s equals to -2. Now let's take a look at frequency response. For example, if h of s equals to s squared plus 100 over s squared plus 2s plus 100, we can specify the numerator and denominator polynomials as b and a respectively. B equals to 1, 0, 100, a equals to 1, to 100. The freq command can be used to compute frequency response function. H equals freq b, a, w, where w is the frequency range in radians per second. Thus, we can plot the magnitude of this frequency response with the following code. And notice that our frequency range is from 0 to 30, and we're plotting the absolute values of h. As we can see from the plot, our function is a notch filter. We often want to plot the frequency axis on a logarithmic scale and select frequency points spreading evenly on that scale. That can be done by adding the following line: omega equals to log space 0, 2, 10. The command will create a set of 100 points spaced equally on a log scale from 10 to the power of 0, which is 1, to 10 to the power of 2, which is 100. We also have to change the last two lines of the code to the following: h equals freq b, a, omega, and semilog x omega, absolute value of h. To plot the values of magnitude of h in decibels, we modify the last line of our code as follows: semilog x omega, 20 multiplied by log of absolute value of h. The phase angle of each of us is plotted by using angle h as the second argument of semilog's function instead of absolute value of h. This will result in the following plot. This plot gives us magnitude of angle in radians. To convert and plot angle in degrees, we multiplied second argument of semilog x function by 180 divided by pi. This will result in the following graph. Thank you for your attention. This concludes the first part of stability and frequency response of linear systems video tutorial.